Okay, hopefully you've already watched the first Gauss's law video, and then this is the harder one, and I'll do two examples. These are probably the most popular, harder examples. And the first one is we're gonna do the insulated sphere again. Insulated sphere, except this time we're gonna make the charge density a function of R. So let's say rho is some function. So rho might be, I don't know, we'll make it 2 plus 5r. Okay, so that what that says is, we look at our insulated sphere, think about what's going on here. Okay, we know that an insulator, the charges can't move, and then in this particular case, there's charge located all the way around and inside this sphere. And this says that the charge density, again, charge density is, in this case, three-dimensional, is coulombs, as a unit of charge, per cubic meter. Okay, and so when like R equals 0, rho equals 2. And let's say this has some radius of, let's say the radius is 3. Okay, so when little r equals 3, meaning you're on the outside, or you're on the edge, then the charge density goes all the way up to 17. Okay, this is kind of numerically kind of working your way through this. So at the inside you get 2 coulombs per cubic meter, and then as you move further and further away, every meter you move you get 5 more coulombs per cubic meter, such that when you get to the edge of this insulated sphere, your charge density is all the way up to 17. Okay, so how do you find the electric field inside? Well, we're going to do the same thing. We're still going to say that the electric flux, which is accumulating that E field over that closed surface dA, still equals the charge enclosed over epsilon naught. The electric field, so we put our Gaussian sphere around this thing, and we've enclosed inside that red Gaussian sphere so much charge. We know that the E field is constant on that, so accumulating all the area is just 4 pi r squared, and that left side is always really easy. And now the hard part. Okay, let's come down here. How much have I enclosed of the charge? Well, I got to accumulate all these little bitty dq's, and so how do I figure that out? Well, I end up having to break this Gaussian, the red Gaussian sphere, into a bunch of shells. So I need to add up the charge on each shell. Okay, and we would call that like a dq. So the summation of all the dq's, dq representing the charge on each shell, then represents the total charge I've enclosed by the red. Okay, so what's dq? Well, dq should be the density of each shell, which we have a formula for, times the volume of each shell, which is dV. Think of differentials in terms of calculus. The differential of volume is dV, which is the volume of each particular spherical shell. So our dq is going to be 2 plus 5r times dV. Well, dV is 4 pi r squared dr, right? As just simply the differential of volume, but it's also the surface area times the thickness. Again, think about a spherical shell here. Think of the surface area times a thickness gives you then the volume of that shell. The volume times the density gives you the charge on each one of those things. So what do we want to do here to find the charge enclosed? We got to integrate 2 plus 5r times 4 pi r squared dr. So we're integrating 8 pi r squared plus 20 pi r cubed dr, and we're going to integrate this from 0 to the r of our Gaussian surface, which is just another little r. I know those maybe shouldn't be the same, but it's fine. So we integrate this, and this is going to get ugly, because this is going to be 8 pi r cubed over 3 plus, that's going to be 20, but then we're going to divide by 4, so it's going to be 5 pi r to the 4th over nothing, because I already canceled that, right? That was 20 over 4. I'll just put a 1 there. Okay, so that's then the charge enclosed. So that's what goes here. So 8 pi r cubed over 3 plus 5 pi r to the 4th all over epsilon naught. And again, this one's going to be really kind of funky on how this all operates. Okay, and so then the electric field inside this monstrosity, that 4 pi epsilon naught is going to be a k. So we get k times all of this stuff, which we can't really simplify, and then the r squared is going to cancel. So it's 8 pi r plus 5 pi r squared, and you get that. Okay, so again, the 4 pi and the epsilon naught became the k. R squared made r cubed r, and r to the 4th r squared, and so you get this electric field, which says inside it kind of grows like some random quadratic. Again, I picked a very difficult case, and then I made the charge density start out at a 2 and then actually grow linearly, which made this thing complicated. And again, if this was just one term, then this would have been one term, but in any way you look at it, the electric field is going to be a complicated thing, because it's not even, I mean, not only is it an insulator, which makes it hard, but it's got a non-uniform density. The charge density grows as R grows, and it turns out that the E field is like that. Okay, now what about on the outside of this silly thing? So we could put a Gaussian surface on the outside of that. Well, then the electric field, it's the same principle here. I'm going to go up here. It's still E times 4 pi r squared, but now we've enclosed the total charge. Well, what is the total charge? Well, think about it. The total charge would be integrating not from 0 to little r, but it's the same thing, except I would accumulate all the dq's from 0 to capital R. If we went numerically, we'd be integrating from 0 to 3. So then you'd have to take this and evaluate from 0 to 3 to find the total charge. And the total charge is just going to be messy. We don't really have to go through all of this, but this is going to be, what, 27, 9, 72 pi plus, what, that's 81. 81 times 4 is going to be, what, 405? Did I do that right? I think so. If I did, it doesn't matter. 405 pi. And all that then is the total charge enclosed, which is just some number, so many coulombs, divided by epsilon naught. And you can still show that the E field is somehow proportional to 1 over r squared. Again, once you get on the outside of this thing, it's somehow like a 1 over r squared. And that number is just the fact that the total charge is just some number. Okay? So that one's obviously a hard one. You're going to have to go through a non-uniform density one. And the other one that I'd like to at least reference is one where you have some charge enclosed, and we'll make it metal. Kind of make things easier. So this is a metal, and on the outside of this, we have a spherical shell on the outside. So this is some sphere, and we'll put it's metal. So the inside metal sphere, let's say it's got a +2 charge. The outside metal spherical shell is neutral, and then we want to know the E field in all these different spots. Okay, and let's say this has a radius of A, and this has a radius of B, inside radius of B, and an outside radius of C. I know I'm getting kind of complicated here. Okay, so we want to know the E field and all these random spots. First of all, we need to talk about the fact that this is going to get some charge induced. So if this is a +2 on that sphere, it's going to induce a -2 charge on the inside of this thing. So all these minuses are going to accumulate, minus charges are going to accumulate on the inside of that spherical shell, and then the outside is going to be left positive. Now again, the shell itself is still neutral. But it's going to be important that a negative 2 comes on the inside and a positive 2 is then on the outside. So let's look at all these situations. What is the E field if R is less than A? Well, if R is less than A, that means we're inside the metal sphere. That's easy. The electric field is 0, because the electric field is 0 inside any metal conductor because there's no charge enclosed. Okay. What if R is between A and B? Okay, so I'm talking about the space in here. Well, then it's just like it's a point charge. The only charge I've enclosed is that thing. So it's E dot dA equals the charge enclosed over epsilon naught. And I get A 4 pi r squared. The total charge enclosed is just that plus 2q. Let's just call that a q. Okay, so that's the q over epsilon naught, and all of a sudden you have exactly what we thought. The electric field is just kq over r squared. Okay, now let's look if r is in between B and C. So now we're inside of this guy. So what's the charge enclosed? Well, the charge enclosed is 0, so the electric field is 0. Those are easy. And then the last guy, what if I'm out here? Well, again, then it's just like it's a point charge. And so R greater than C, the electric field is just like a point charge, and so it's just KQ over R squared. And so the graph of this thing would be really weird. The electric field is a function of R, so it'd go this way, it'd be 0 all the way until you got to A. So it starts out at some value here, and then it'd fall off like a 1 over R squared. But then once you got to B to C, there's no field inside that thing, so it'd be like this. And then once you got to C, it'd kind of pick right back up at that curve where that curve should be, not at the same height, but over here. And then it'd fall off like 1 over R squared and go to 0. Okay, makes sense? So you can look at all these different regions. And we could have made this differently, but certainly you get some induced, they would talk about this negative charge here, right? This induced charge on the inside of that shell. And then you just got to kind of think through this. There's actually 4 different regions of space here. 2 of them are just like point charges, and 2 of them the electric field is equal to 0. So just kind of take your time and think about it. They both could be charged. One could be a negative charge, one could be neutral. You know, you just have to kind of think that through and then go through Gauss's law for each one of those things. But again, lots of times the E fields are zeros, or they're acting like a point charge. When they're insulators, things kind of get funky because then you have to actually think about how much charge you've actually enclosed. Okay, the last thing, the AP likes to ask questions like, what about the charge density? What about the sigma on the inside versus the outside? And think about, where is the charge more dense on the surface, on the inside or on the outside? And think about, well, if these two are the exact same, this is a negative 2 on the inside and this is a positive 2 on the outside, well, the inside is going to have a smaller surface area of 4 pi b squared, and the outside is going to have 4 pi c squared. And so the charge density of the negative will actually be slightly greater in magnitude than the charge density of the positive, and that would just depend on the differences between B and C. So sometimes charge density of B in magnitude is actually going to be greater than the charge density of C because they have the same charge and B's got a smaller area, so it's going to have a higher density. They like to ask questions like that too. Okay, hopefully this helps you on some of the harder ones.